we're going to finish off 3.3 and then hopefully do all of 3.4 today. We'll see. 3.4 is just putting all the pieces together, which we've kind of been doing already. So what we observed yesterday was that if I have an equation in this form, where I have something that's multiplied out in front of my function, so some number that's multiplied out there. Hello, hello. Oh, there we go. I am on. Just seems quiet to me. That's going to be the vertical stretch factor. So again, if it's negative, that just means the reflection. So we take the negative as a reflection, then we're done with the negative and we only think about the size of the number. The size of the number will give us the vertical stretch factor. Then, if there's something multiplied to the b, then just like with a translation, it does the opposite of what it looks like. So instead of multiplying all the x values by b, all the x values are being divided by b, and so the stretch factor is 1 over the absolute value of b. Again, if there's a negative, we'd say it's a reflection in the y-axis. And then the stretch factor is just the size of the number. Question? So the question is, why is it the opposite? And I will attempt to answer, but again, this will not make sense to everyone. Here's what's happening. So let's start with, suppose we're looking at y equals the square root of 4x. If I pick an x value, so I pick an x value of 1. I'm thinking of a different way I could try to explain this. Let's see what would happen. Suppose I have my handy-dandy little function machine here. So this function machine takes whatever input there is, and then it's going to square root that number. So that's going to be, it's going to take the x, it's going to square root it, and what I get out is going to be whatever the square root of x is, right? So if I put a 1 into this function machine, the 1 goes into the square root, I square root the 1, and what I get out is a 1. If I put a 4 in here, then the 4 goes into my machine square roots it, and what I get out is a 2. Make sense? Okay. So suppose I have this other function, and what's happening? Well, no, let's not think of another function just yet. So ignore that one. We'll come back to this one. Suppose instead, to begin with, I'm going to take whatever x value I get, and I'm going to multiply it by 4. Then I'm going to stick it into the machine. So my machine is going to take a number that's 4 times as big, and it's going to look at that, and it's going to make that the y value that goes with this original x. So visually, what's happening? So now let's look at what I highlighted up here, the y equals the square root of 4x. If I was to take 1 and plug that in, so I'm going to erase this. I'm going to say, suppose what I'm plugging in is a 1. What I'm square rooting is 4 times 1. So I'm not just getting the square root of 1 out, I'm getting the square root of 4 times 1, which is going to be 2. So I'm sticking 1 into the red function. What happens is this 1 gets multiplied by 4. And so it's looking over here when x is 4 to see what is this y value. This y value becomes the new y value for when x is equal to 1. So I put in a number. My function looks 4 times as big to see what was that y value that's 4 times as big. And it takes that y value and it makes it the new y value when x was 1. That's what's happening. And as I said, that may not make sense to many of us. Fortunately, we can just memorize at this point. And the memorizing would say, whatever looks like it's being done to the x, the opposite is being done to the x. So, looks like my x's are multiplied by 4, but in terms of the graph, all my x values, I should say all my y values, nope, all the x values are a quarter as big for the same y value. So here, these y values, I kept the same. All the x values are 1/4 as big. So this x value of 4, now 1/4 as big, and it's at 1. This x value of 16, now it's 1/4 as big, and now it's 4. That's what's happening to the graph. So we say the graph is stretched horizontally by a factor of 1/4. And that's as good as I can do for today. Okay? So again, the general rule is whenever you have parameters, stretch factors, or translation terms, it does the opposite of what it looks like when it's grouped with a variable. And that's typically with the x's. So let's try this question, number 5. We're given the graph y equals f of x, and it's the solid line that's drawn, and then its image. So whenever we do a transformation, we talk about the original shape as the object, and the result after the transformation is the image. So those are some terms that are used, and in physics you may have talked about that when you talked about reflections. So when you had a mirror or something and you were looking at where things were reflected, you had the original object. What you're looking at in the mirror is an image that's the same distance on the opposite side of the mirror. And that's kind of how a reflection works. So we want to write an equation and a mapping to describe the transformation. So first I would look at this and I would ask myself, are there any reflections? So I look at the shape of this original thing that I have here, kind of goes up and then down, horizontal and up. And then I look at the image, it goes up and then down and then horizontal and then up. Oh, it kind of has the same orientation. So I'd say there's been no reflection. So it's still in the same orientation as it was initially. So my A and B values are both positive. So that's great, no reflection. So then I'll think about stretches. And what I'll do for the stretch is I'll look at some key points and see how distances between those points have changed. So for example, if I looked at, let's say, well, let's do this horizontal line part here. That original horizontal line was too long. And then I compare that on the image and I see, oh, that corresponding part is now 1 line long. So it's half as big. So that tells me it's been stretched horizontally by a factor of 1/2. And then I'd probably check another pair of points just to confirm it. So I would look at maybe this endpoint, that endpoint. On the original, that distance was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I look at it on the image. This point, that point, 1, 2, 3, 4, 5. Yes, it's half as big. Cushman, do you have a question still? Okay, Probleen. The stretch factor is 1/2. So the stretch factor is describing what's exactly happening. I have not written the equation yet. I have not written down what the A or B values are. Yes? That is what it says. So given this graph, the solid line, okay, then we'll do something similar as we look vertically. So let's say I look at the lowest point and the highest point, and I see it's 1, 2, 3, 4. Okay, so my original height was 4 units, and then I look at my image. So I'll say from here up to there, well, it's kind of off the map, so we'll see. It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it looks like it's 3 times as big. Let's double check with another pair of points. So suppose I do from here to there. That height was 3. Look at the corresponding points. Here to there, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, it's 3 times as big. So I have a vertical stretch. So I'm going to word it slightly differently because there are different ways, different orders of the words. So I'll say it's a vertical stretch. Sometimes we say it's about the x-axis. I'll leave that out now. By a factor of 3. Okay? So, yep, we could do the very top point. I'm just a little bit hesitant because it's off the grid. And yeah, I think it's one grid line, but I'm going to check somewhere else as well. Okay, then as we look at the information we had in our summary up here, if I have a vertical stretch about the x-axis by a factor of a, then that a value just gets multiplied in front of the function. So I had a vertical stretch by a factor of 3, so my equation, y equals, here's my f of x, my a value was 3. Then I look up here again. If it's stretched horizontally by a factor of 1 over b, or absolute value of b, then I have a b multiplied to the x. So what goes in here is the reciprocal of that stretch factor. So if the stretch factor is 1/2, the reciprocal of that is 2, so that tells me my b value is equal to 2. So I'll have 2 times the x, and that will be the equation for the stretched function. Questions with that? Nope. Well, next page. Probleen. Oh, we're supposed to do mapping as well. Yes. And aren't you supposed to be taking off your extra layers? Yes, you are. So please do that. But yes, I will give you a candy for that. So yes, please take off extra layers to get into uniform. Thank you. Okay. So here we're given a domain and range, and we want to state what the new domain and range is after. Oh, yeah, back to that question. It's like I just lost my mind. Maybe I should just go home and go to bed. That'd be good. Pretend I have COVID. Boy, I could have given another candy away there almost. Whoa. Okay. Mapping notation. And let's do blue here. So we have our points, x comma y. What happened to all the x coordinates? x values were multiplied by 1/2. So x values are actually multiplied by the stretch factor. They're not multiplied by the b value when we're talking about what's happening to the points. So the stretch factor was 1/2. So here, all my x values end up being half as big. My y values, stretch factor was 3. So all my y's are multiplied by 3. And again, we could test it out. So I could pick a point on my original. Suppose I just picked this point. It was negative 1, 2, 3, 4, 5, 6. Negative 6 comma 2. And then see what happens to that under the mapping I wrote, just as a way of verifying. So negative 6 comma 2. Negative 6 times 1/2 would be negative 3. 3 times 2 is 6. So negative 3 comma 6, is that where that point ended up? And I look, negative 1, 2, 1, 2, 3, 1, 2, 3, 4, 5, 6. There we go. Negative 3 comma 6. That's where that point was mapped to. Todd. It's 3, yes, because the a value is the vertical stretch. And the b value is the reciprocal of the horizontal stretch. Robleen, are you happy with this? Okay. Thank you for keeping me honest here. Now we'll try this question. So stretch vertically by a factor of 1/2. Does that change domain or range or both? Oh, I'm sure some of you were right. I just couldn't hear. Range. Thank you for being a little louder. Range. Louder is enough for a little bell. Oh, I went up and got my other gong yesterday. So now I have 2 gongs. Ah, yes, this is a gong show. There's my little gong. And my bigger gong. Yes. But I'm open to receiving more gongs. If any of you, birthdays coming up, Christmas, or just, no occasion, just Mr. Wagner, I just wanted to get you a gift. There you go. So just thought I'd throw it out there, and I guess I've recorded it for future use there. Okay, so yes, range is changing. So my range these y values just get multiplied by 1/2. So it's just going to be negative 4 comma 1. And the endpoints stick with the original term that they had. Horizontally by a factor of 2/3. So again, when we're given stretch factors, that's telling us exactly what's happening to x's and y's. So my x's will be multiplied by 2/3. So 2/3 of 6 is 4. 2/3 of 12 is 8. Oops, round bracket. Yes.
Stretching by a factor of 2/3, don't you?
If I'm stretching by this, that tells me my b value is 3/2. But my stretch factor tells me what's actually happening horizontally and vertically. So again, as we look back at this question, here we said we were stretched horizontally by a factor of 1/2, and that's what happened. This distance ended up being half as much. Okay, so the stretch factor is describing what's actually happening visually and to the x coordinates. It's only in the equation the b value is the reciprocal. Okay. Yes. On that side of the equation, yes. Yeah, so then we just rearrange. But that's a good point because if I was to rearrange this, it would look like y over 3 equals f of 2x. And what I've been saying a number of times is when that stretch factor is grouped with a variable, the stretch factor is actually the reciprocal, right? So instead of all the x's being multiplied by 2, they're all divided by 2. They're all half as big. The same thing happens here when that parameter is grouped with the variable it's affecting. It does the opposite of what it looks like. So the y values aren't 1/3 as big. They're not divided by 3. They're actually 3 times as big. So if we were always to rearrange it so that the parameter that is with the variable it's affecting, it would always be doing the opposite of what it looks like. It's just because we generally rearrange the equation into this form, what's affecting things vertically does exactly what it looks like because it's not with the y, it's on the other side of the equation. And the x, the parameters with the x, those we can't move. They have to stay in the bracket inside the function. Years ago, when we taught more things about circles, so when we get to the trigonometry chapter, we're going to look at x squared plus y squared equals 1 will be the equation for a unit circle. And if I replace this x squared with an x over 2 all squared, this would be kind of like if I had a half times x. So this would mean it would be stretched horizontally by a factor of 2. So the original, let me go with that, that would just be a circle centered at 0, 0. And it goes here at 1, there 1, here -1, there -1. But if I put x divided by 2 like this, that would say it's stretched horizontally by a factor of 2. So now it's going to come out here to 2 and there to -2. And I actually get, whoops, an elliptical shape, kind of like that. So when my circle gets stretched out, that's a horrible looking ellipse, but you sort of get the idea. That's what the result would be. Similarly, if I put y over 3 in brackets and then all squared, what would happen? The y values are stretched by a factor of 3. So there's 2, there's 3, it would actually go up there, and then would come out here, and then down here to -3. And then we'd get a vertical ellipse, kind of like that. In this situation, kind of an equation like this, isolating the y is not a simple thing to do. It's not a function. So I end up with plus or minus square roots, and it just looks complex. So typically we would just write it in this form. And then we could see how things stretch or compress. Stretch is a better word. Stretch bigger or stretch smaller based on the number that's multiplied or divided to that x or y value. We don't get into that in this course. In some previous versions of the grade 12 math, we did things like that. Okay, let's move on to number 7. And for number 7, the 2 that's in front here, will it affect the domain or range? Ooh, I will count down and then you will holler to me. Domain or range, 3, 2, 1. It's only this. Okay. If there's lots of volume and energy to it, then you get the gong. And I'll have the medium gong for the medium amount of energy and volume. We'll just keep this one handy too. Okay, yes, that's going to affect the range. Will the y values get bigger or smaller? Well, that's actually not a good question. Will they be multiplied by 2 or divided by 2? Oh, nice. I didn't count down or anything. That's good enough for a little gong. So my range multiplied by 2. So negative 16, comma 4, keep the brackets in the order they were. So that means this 3 is going to affect the x's. Do the x's get multiplied by 3? I should say the x values, as in the domain, multiplied by 3 or divided by 3? Oh, we're getting close. I'm going to say, oh, I want more yet. Get multiplied. So domain was 6 times 3, 18. 12 times 3, 36. Good? Okay. Mapping. So my original domain, I'll rewrite here just so I can see it. Was 6 to 12. And my range negative 8 to 2. Well, here's an interesting side question. Could you draw a graph of a function that has this domain and range? This has nothing to do with what we're doing. Well, it sort of does because we have this domain and range. But what might it look like? I'm going to give you a minute. What might the graph look like if I have this domain and this range? Find a little corner of your paper. We're not using lots on this page anyhow. Who has a graph that would work? Anybody? A graph that could have this domain and range? Anybody? Nobody came up with one? Oh well, guess we'll just do the question. So with this mapping, this half times x, what is that going to do to my domain? Are the x values going to be, are the x values going to be multiplied by a half or multiplied by 2? Oh, that's good enough for a soft big gong. Multiplied by a half. This is true. What color did we do? 3 and 6. Okay. Now for the range, we have both a reflection and a stretch. We could treat them separately, or we could just do it all at once. So, all at once, will our y values in the range be multiplied by negative 3 or divided by negative 3?
Multiplied by negative 3!
multiplied by negative. Okay, so people in video land, I don't know at what point you lost it, and sorry about the static there. This mic does more static, and if I want to record, that's just going to happen. Sorry, Glenn, you're right there. Kind of irritating. So, this is giving me the numbers for the range, but it's still not written right. Nathaniel, I think you wanted to correct me. -6 goes first, and then 24, like that. Oh, yes, well done. The brackets need to travel with the numbers. So the closed interval needs to be with the -6, and the open end of the interval with the 24. So this would be our new range. Good. Questions? No questions. Yes, Vinia. So I'm not multiplying by 3 over x. I'm multiplying by 3. The location of that 3 is telling me it's affecting the x's. Okay, but the x, that's just kind of talking about the horizontal aspects of the graph. And so I just look at the 3 where I have the 1 over 3. Reciprocal of that is 3, so the stretch factor is a 3. Uh-huh. Yes. So you always multiply by the reciprocal. Other questions? All right. That finishes this lesson. So I'm going to have you look ahead to the next page. It starts with warm-up questions. So try these, putting together a variety of transformations. And I will stop this video.